there are two cross resistant, four actually, cross resistant, I think.
I'm just going to show you the working principle of this bridge and how we can use it on the strain gauge measurement. So just wait for a few minutes and then you'll be satisfied.
Thank you, Professor. And also, would you please record the class?
Yes, thank you that you remind me. Okay, let's start our class. Today's class is mainly on the Wisdom bridge for strain measurement. When I'm referring to strain measurement is, of course, the strain measurement that could be possible when using resistance-based strain gauges. Okay, as we already discussed about, when dealing with strains, we are going to measure strains of order of magnitude of some hundreds, okay, of microstrains. So approximately the strain could be of this order of magnitude, about 10 microstrain, okay. Thus, that means that if we are having a base resistance of about, let's say, 100 ohms, as we discussed last class, should be 120, but now just to refer to order of magnitude, that means that the change of the resistance, that if you remember is given you by this formula in which R is the base resistance, K is the strain gauge factor, and epsilon is the strain that has been estimated. This means that the value of the change of the resistance is about 2 times 10 to minus 2 ohms. That is a very small quantity. Okay, for example, to be measured using the tester, the multimeter that could be commonly available off the shelf in a grocery store or whatever. Okay, so that's the reason why we need a more sophisticated measuring circuit, and this is the Wisdom bridge. Wisdom bridge based on a constant that I'm going to write here, constant voltage. Okay, there is also a different circuit, measuring circuit that is based on constant current. We are not going to see it, just refer to the constant voltage working principle. So let's write down the typical electrical circuit that is representative of your Wisdom bridge. So we got 4 resistors that are connected in this way. Okay, we have 4 resistors. We can name them as R1, R2, R3, and then R4. This circuit is fed by an input voltage here, like that. And the value of the input voltage is V. And then we are going to measure the output voltage of this bridge. And the output voltage is E star. Okay. That is what is typically referring to a Wheatstone bridge. As you can see, we have a grid of electrical resistance, R1 to R4. There is an input tension, input voltage, V, and we're going to measure the E. Now, we have to refer to the Kirchhoff law, the two Kirchhoff's rules, the first and the second, I don't know if you remember, in order to try to explicit the different electrical parameters that are affecting our electrical circuit, the bridge, Wheatstone bridge circuit, in order to have a relation that is linking the input, that is the strain gauge, resistance variation, and the output tension E, that is E star. So the basic idea is you can figure out that instead of having just a resistance, we are using one or more than one, up to four, of course, resistances that are your strain gauge. But now, before introducing the strain gauge, let's try to solve this circuit, this electrical circuit. So in order to do that, let me call the current flow, electrical current flow that is flowing in the upper part of this electrical grid. So we can call that as I1. And the lower part is I2. Okay. We can name the nodes as node A, B, C, and D. Okay. And then what we got is that we can say that the differential of potential between nodes A and B, that I can refer to as BAB, is equal to the flow, the electrical flow passing through R1 times the value of the resistance, R1. So it is I1, R1. As well as the differential of potential between nodes A and D is equal to I2, R2. Sorry, R4. Okay. How can we get the values of the currents I1 and I2? In order to do that, we can say that if we refer to the nodes A and C, what we are having is that the input tension D, okay, is equal to I1 times the equivalent resistance, because we are having a series of resistance. The resulting value is the sum of these two resistance. So I1 times R1 plus R2. And always we can say that the output tension, the input tension V is also equal to I2 times the relative equivalent resistance. So R3 plus R4. Thus, we can use these last two equations to identify the current flowing in the upper and the lower branch of this resistance grid. So what we are having is I1 is equal to P over R1 plus R2, and I2 is equal to V as well, divided by R3 plus R4. Okay. If we plug these two equations, the two information concerning the electrical circuit, into the previous one, what we can say is that AB is equal to the I1, that is B over R1 plus R2 times R1, and the AD equal to B divided by R3 plus R4 times R4 times R4. Okay. That is what we got. Now, remember, the working principle of this Wheatstone bridge is try to measure the output tension E star when the circuit is fed by the input tension V, and because there is a change of resistance R1, 2, 3, or 4, whatever. So in order to find out the output tension E star, we can use these differential potentials between nodes A, B, and AD in order to have the E star. So what we can say is that the output tension E star is equal to the the differential potential between node B and D from your Wheatstone bridge circuit, as you can see. And this is the algebraic sum of the two differential potential between AB and AD. That is AB, BAB, negative BAD. That means that your E star is equal to R1, R3, negative R3, R2, R4 divided by R1 plus R2 times R3 plus R4, everything times the input tension. Okay, and that is very nice equation. Okay, because it links the output tension E star to the input tension V, but also to the electrical parameters that are characterizing your Wheatstone bridge circuit, specifically the resistances are 1, 2, 3, and 4. Now, a question for you. Is there a specific electrical resistance configuration that allows me to have zero output tension E star, whatever is the input tension V? That is, E star is equal to 0 if R1, R3 is equal to R2, R4. Whatever will be your input. Okay, and that is a very, very interesting configuration concerning the values of the electrical resistance, because whatever will be the input, the output tension E star will be always 0. And that is so interesting, so important, that is the starting point for the strain gauge measurement. This relation between the resistances is called the balancing condition, and that is very, very important to be remembered. Okay, so please open your DNA code and input that equation that is referring to the balancing condition. Okay, what does it mean, the balancing condition for a Wheatstone bridge? It means a specific relation between the electrical parameters of your Wheatstone bridge, that is the resistances here, so that if that condition is met, then the output tension is always 0, regardless the input tension. So now go back to the equivalent operational circuit here, the Wheatstone bridge. And as you can see, we can think to use that circuit in your strain gauge measurement just by substituting or by using one leg, two legs, three legs, or four legs, so are 1, 2, 3, 4, okay, as the resistance corresponding to the strain gauge. So how is the working principle of the strain gauge measurement used in the Wheatstone bridge? So first, what we have to do is put one strain gauge on one leg, okay, of the Wheatstone bridge. So, for example, R1 is your strain gauge that is bonded to the host structure, and then it is connected using wirings to the Wheatstone bridge. Okay. Then change the other resistances, R2, 3, 4, so that we set the balancing conditions. Okay. That means we are changing the value of the other resistances, 2, 3, 4, so that balancing condition R1 times R2, R4 is met. That is, the output tension is 0. Then what? Then we apply whatever load to your structure. As a consequence, there is a strain, and because you have bonded the strain gauge to the structure, that structure strain is transduced by the strain gauge device as a change of resistance. And because of that, there will be an output tension, the Wheatstone bridge is 0, different from 0, because the balancing conditions are not more satisfied. Okay, so the third point is we are having a strain. Okay, because of the strain, there will be the output tension that is no more 0. Once again, that is true because of the strain. The structural strain corresponds to a change of resistance. We saw that in the last classes. Because there is a structural, because there is a change in the electrical resistance, the Wheatstone bridge balancing condition is no more met. And therefore the output tension is different from 0. Then the last point, 4, is to estimate the strain that is the origin of everything from the measurement of the output tension. Okay, so this is the general working principle of your strain gauge measuring chain when using the Wheatstone bridge configuration. Okay, so just going back a little bit, this is the Wheatstone bridge configuration. Please note that I can name the resistances 1, 2, 3, 4 as you prefer. I mean, there is not a given rule to name the resistances. Generally, this way of naming the resistance is the most common one used. Okay, and please refer to the legs where we are having to the nodes, sorry, where we have the input tension and the nodes where we are having the output tension. Okay, so we can have a rotation of the visualization of this Wheatstone bridge configuration, but however, the meaning of the legs is the same. Okay, and then you can name these resistances as you like. So the step now is how can we relate this output tension E star to the strain?
Professor.
Yes.
What do you mean by leg? Do you mean we can remove R1 and put a strain gauge on it, or?
Yes, the leg, here we are having 4 legs, the leg AB, leg BC, leg CD, and leg DA. So in principle, we can have strain gauges in place of R1, in place of R2, R3, and 4. Okay.
And then we will find a condition which have balancing condition. After that, we will change one of the resistance. Am I right?
Yes. You have to, the balancing condition refer to the Wheatstone bridge in the reference condition. No loading, no everything. Okay. So 0 strain. Okay.
And what we do after that?
Yes, once you have your Wheatstone bridge in the reference condition, okay, you can have the values of the resistances, if you set the Wisdom bridge in the balance condition, then the resistances R1 times R3 should be equal to R2 times R4. Okay, so you can choose whatever strain gauge that you like, but if you would like to have a balance condition, then that equation should be satisfied. Then second step or third step, third step, you apply an external load. As a consequence, there is a change of resistance somewhere in the legs, and therefore the Wisdom bridge is no more balanced. That is, the output tension E star is different from zero. Okay? So the task of your measuring chain now is to estimate the strain from the estimate of E star, so the output tension.
Okay, thank you.
Okay? Now, let's assume that we are having all the legs with some strain gauges. So we are having a total of 4 strain gauges. Okay. And therefore, there exists with different value from 0 all the change of the resistances in the 4 legs. So delta R2, 1, R2, and R3, and R4. Okay, all of these changes are different from 0. Okay, because we are having a strain gauge measurement. I can prove you that the output tension delta E star from the balance condition, that is from 0, could be written as this equation: A over B times the input tension D, in which A is equal to R1, R3 times delta R1 over R1 negative delta R2 over R2 plus delta R3 over R3 plus delta R4 over R4. And the coefficient B is given you by R1, R3 times R1, R2, everything multiplied by R1 plus R2 square, everything. Okay. So if we plug this information concerning the coefficients A and B into that general equation, what we can say is that the change of the output tension delta E star is given you by R1, R2 times R1 plus R2 square times delta R1.
Professor?
Just one second, let me end the equation. R2 plus delta R3 over R3 delta R4 over R4, everything times 3. And finally, if I am defining lowercase r equal to the ratio of R2 over R1, what we got is this general equation. The output tension, the change of the output tension, delta E star, is given you by R over 1 plus R square times delta R1 over 1 negative delta R2 over R2 plus delta R3 over R3 negative delta R4 over R times the input. And that is the fundamental equation for the strain gauge measurement that you have always to remember. And this equation is valid when we are having small variation, small values of the change of the resistance. That is, it is true if your strain is less than approximately 0.01. Okay. If you remember that we are using microstrain, okay, that is equal to about some thousand microscale. Okay, question?
Yes, Professor. Why did we get negative sign in the change in resistance of R2 over the
Because
normal
of the
resistance?
circuit. Because of the circuit. If you want, I can prove you that, but it takes, let's say, 2-3 pages. So believe me, it is what we are having. Okay.
Okay.
And
Okay, Professor.
by the way, if you can see there is a double the change of sign corresponding to R2 and R4. Okay. If you go back to your general equation, R2 and R4 are the opposite resistances, opposite with respect to the leg positions, okay, in your wisdom bridge. And R2 and 3 are again opposite positions. Okay, that is why it is not important the name you are giving to the resistance, but the positions, the relative position in the wisdom bridge. So be sure
You said
to,
R2 and R3 are opposites?
yeah, R2 and 3, sorry, R1 and 3 are opposite.
Okay.
And 2 and 4, sorry if I said that I was wrong. Okay. Now, another important thing concerning the strain gauge measurement, okay, is that is related, if you want, to the fact that the negative signs could be misleading. Okay, just to have an example with you. Let me assume to consider once again your wisdom bridge like this. Let me assume to have 4 strain gauges, equal strain gauges. So R1, 2, 3, 4 are equal strain gauges. And I want to measure these, to measure the strain using these 4 legs wisdom bridge for a cantilever beam or for a, let's say, for a plate, doesn't matter. Now, let's consider, for example, the beam or the plate, so a portion of the structure, something like that. Okay, could be a plate, could be a beam. Now it's not the point. And I would like to know the strain value here at this point of the structure, for example. If now I am using 4 strain gauges in the way that I just told you, let's assume to plug, to bond these strain gauges here, 1, 2, 3, and 4. Okay, these very tiny piece of lines are representing your strain gauges. And assuming that these lines are so tiny that are approximately sensing, transducing the same strain, it is not true from the physical point of view. But let's assume that they are having the same strain field that are measuring. Okay. Now, if I am using the previous equation, what it means that if I have in 4 strain gauges like there, the output tension delta E star is 0. Because the change resistance R1 is equal to the change resistance R2, that is equal to R3, because, as I said, same strain gauges and practically the same strain measurement. So everything is equal. The output tension is 0. Therefore, we can't have a measure of the strain. Okay. So according to your, let's say, imagination, your feeling, how can we take a measurement using, for example, 4 strain gauges in this way? Do you have a clue? Can you see the solution to this point?
Measure them individually.
Say it again, please.
Measure them individually.
Yes, but if you're doing that, that means that you are just using one resistance at time. That is, in your equation, you are neglecting 3 out of 4 terms, and then you are having the measurement. Yes, that is true. You can do that. That is the typical quarter like measurements condition. But I would like to have all 4 strain gauges. So how can we do that?
We can neglect only one of them and calculate the other one.
No, but if you're doing that, you are having not you're not using 4 strain gauges at the same time. You are using 4 strain gauges one time after the other. We can do that. That is a quarter bridge configuration. We can do that. But now I would like to have all 4 of them active in order to take the kind of measurement. Other clues, other ideas about that?
Can you make your question, a bit clear for me? I really didn't understand very well.
Yes, the question is, considering the previous equation, the bracket equation, and considering that I would like to measure the strain using 4 microstrains, 4 strain gauges like the one that I draw on the picture, okay, how can I do that? Because if I'm doing that, then the output tension is 0. So I can have any information at all. So the question is, how can I use 4 strain gauges at the same time to measure the strain? No, not at all.
Wait, so we said that according to the balancing condition that R1, R3 equals R2, R4. So if we just have resistance that I guess that violates that balancing condition, would that work?
Almost there. I mean, you have to remember, you have to use your knowledge in structure. Okay, so if you pass the exam structure so far, then you can say that, for example, at this point, okay, we have, let's say, compressive strain in this upper part of the structure, whatever it is, and tension strain of that structure, the lower part of the structure. Okay, what does it mean? It means that if I would like to have the same, if you like to have 4 strain gauges at the same time to measure the strain there, then I have to refer to this measuring configuration. For example, 2 strain gauge at the bounded at the upper side, 2 strain gauges bounded at the lower side. Moreover, because of the equation, you have to use, let's say, R1 here, R3 there, and R2 there, and R4 there. Okay? So that we are playing, if you want, with different sign of the strain, positive, negative, and with a different relative position on the Wilson bridge. Okay? Of course, is the same happens when you are willing to use just 2 strain gauges at the same time. So if you want to have the strain gauge measurement with just only 2 strain gauges, okay, if you're using R1 and R2 there in that configuration, then once again, you are having that the output tension will be always 0, whatever is the strain. On the contrary, if you are having the strain gauge positioning in this way, let's say R1 and R2, then the output tension will be different from 0. Okay, so that's the reason why when bounding, when locating, when using the strain gauges, you have to know what type of strain is characterizing your measurement in your structure, then you have to use a proper number of strain gauges so that it maximizes as much as possible the sensitivity. We are going to see that in a few seconds, okay, of the measurement. But you have also to take into account what's happening there in order not to have zero output tension. So your measurement is completely useless. Okay. That's the reason why that this equation, the bracket one here, is generally rewritten as a summation of all the resistance, because we are implicitly considering that when you are using them, we are all using with a smart vision. I mean, positive, negative are in the right conditions. Okay, so we can rewrite that equation as delta E star over the input tension is equal to lowercase r over 1 plus r squared, and then the summation from index n of delta Rn over Rn, okay, in which n is the number of active legs, that is the number of legs in which we are having the strain gauge for the measurement, and we are also implicitly assuming that you are using the right legs and the right position on the structure in order to avoid self-compensation so that the output tension is zero. For this reason, we are having the possible values of the active legs in the operating condition, that is 1, generally referred to a quarter bridge configuration, just one strain gauge, and equal to, that is half bridge configuration, and finally n equal to 4, that is full bridge configuration. Okay, number 3 is not used because you can do anything. You can say anything. Okay, so 1, 2, 4, quarter bridge, half bridge, full bridge configuration. 1, 2, 4 strain gauges that you are using at the same time to measure the strain in one point. There are differences. We will see next class what is this difference in the usage of different active legs. Okay. Now, if you remember, your delta R over R was defined as the K strain. You remember last class output. Okay. So if you refer to the nth active leg, we can rewrite that equation as your delta E star over V is equal to R over 1 plus R square n Kg epsilon, in which Kg is the global strain gauge factor that takes into account whatever effects that we saw together last time. Okay, once again, n is a number, 1, 2, or 4, depending on the active legs. Kg is the number, is the strain gauge factor, okay, and the n is also called the resistance ratio, okay, that is related to the electrical efficiency of your bridge circuit, Wheatstone bridge circuit. Okay, questions on that?
R over 1 plus R to the power 2 is resistance ratio?
Yeah, 1 plus R to the power of 2. Of course, if you look to these two, to compare these two equations, this one and the last one, I am assuming that you are using the same strain gauges for each leg. Okay, same series, of course, same type. Okay, same basic electrical resistance, same behavior, same everything. Okay, otherwise you can't write that equation because you can't change the summation sign with the number of active leg n. Okay. Okay, time is over, I think. So,
Professor,
yeah,
sorry. If we have 4 strain gauges, we have 4 measurements. So what is the benefits? I think we can do it with 2 different measurements.
you are not having 4 measurement. If you go back here to the general layout, Wisdom Bridge layout here, what I'm saying is that you have an output tension, so just one measurement that takes into account the change of resistance because we are using a number of active strain gauges that are measuring the same strain. Okay, we will see the
Yes.
benefit. We will see the benefit of using just 1, 2, or 4 strain gauges next class. Time is over. I can go on now.
Thank
You
you.
have to wait this weekend. Please wipe your tears because you can't have the end of the story now. I know that you are a little bit upset. Your heart is beating so fast that you can't stand this, but please do that. Okay. On Monday, I'll tell you the end of the story.
Thank you, Professor.
Okay. Can you survive till Monday?